In number theory, the fundamental theorem of arithmetic, also called the unique factorization theorem or the unique-prime-factorization theorem, states that every integer greater than 1 either is prime itself or is the product of prime numbers, and that this product is unique, up to the order of the factors. For example, 1200 equals 24 times 31 times 52 equals 3 times 2 times 2 times 2 times 2 times 5 equals 5 times 2 times 3 times 2 times 5 times 2 times 2 equals etc. The theorem is stating two things. First, that 1200 can be represented as a product of primes, and second, no matter how this is done, there will always be 4 2s, 1 3, 2 5s, and no other primes in the product. The requirement that the factors be prime is necessary. Factorizations containing composite numbers may not be unique. This theorem is one of the main reasons why 1 is not considered a prime number. If 1 were prime, the factorization would not be unique, as, for example, 2 equals 2 times 1 equals 2 times 1 times 1 equals. History. Book 7, Propositions 30 and 32 of Euclid's Elements is essentially the statement and proof of the fundamental theorem. If two numbers by multiplying one another make some number, and any prime number measure the product, it will also measure one of the original numbers. Euclid, Elements, Book 7, Proposition 30. Proposition 30 is referred to as Euclid's lemma, and it is the key in the proof of the fundamental theorem of arithmetic. Any composite number is measured by some prime number. Euclid, Elements, Book 7, Proposition 31. Proposition 31 is derived from Proposition 30. Any number either is prime or is measured by some prime number. Euclid, Elements, Book 7, Proposition 32. Proposition 32 is derived from Proposition 31. Article 16 of Gauss' Disquisitiones Arithmetici is an early modern statement and proof employing modular arithmetic applications. Canonical representation of a positive integer. Every positive integer n greater than 1 can be represented in exactly one way as a product of prime powers, where p1 less than p2 less than pk are primes in the alpha I are positive integers. This representation is commonly extended to all positive integers, including 1, by the convention that the empty product is equal to 1. This representation is called the canonical representation of n, or the standard form of n. For example, 999 equals 33 times 37, 1000 equals 23 times 53, 1001 equals 7 times 11 times 13. Note that factors p0 equals the first of may be inserted without changing the value of n. In fact, any positive integer can be uniquely represented as an infinite product taken over all the positive prime numbers, where a finite number of the near-positive integers, and the rest to 0. Allowing negative exponents provides a canonical form for positive rational numbers. Arithmetic operations. The canonical representation, when it is known, is convenient for easily computing products, GCD, and LCM. However, as integer factorization of large integers is much harder than computing their product, GCD or LCM, these formulas have, in practice, a limited usage. Arithmetical functions. Many arithmetical functions are defined using the canonical representation. In particular, the values of additive and multiplicative functions are determined by their values on the powers of prime numbers. Proof. The proof uses Euclid's lemma. If a prime p divides the product of two natural numbers a and b, then either p divides her or p divides b. Existence. We need to show that every integer greater than 1 is a product of primes. By induction, assume it is true for all numbers between 1 and n. If n is prime, there is nothing more to prove. Otherwise, there are integers a and b, where n equals ab and 1 less than a b less than n. By the induction hypothesis, a equals p1 p2, pj and b equals q1 q2, qk are products of primes. but then n equals ab equals p1 p2 dot pj q1 q2 qk is a product of primes. Uniqueness assume that s greater than 1 is the product of prime numbers in two different ways. We must show m equals n and that the qj are a rearrangement of the pi. By Euclid's lemma, p1 must divide one of the qj, relabeling the qj if necessary. Say that p1 divides q1, but q1 is prime, so its only divisors are itself and 1. Therefore, p1 equals q1. So that reasoning the same way, p2 must equal one of the remaining qj. Relabeling again if necessary, say p2 equals q2. Then this can be done for each of the m pi's, showing that mn and every pi is a qj. Applying the same argument with the s and s reversed shows nm and every qj is a pi. Elementary proof of uniqueness. The fundamental theorem of arithmetic can also be proved without using Euclid's lemma, as follows. Assume that s greater than 1 is the smallest positive integer which is the product of prime numbers in two different ways. If s were prime, then it would factor uniquely as itself, so there must be at least two primes in each factorization of s. If any pi equals qj, then, by cancellation, s pi equals s, qj would be another positive integer, different from s, which is greater than 1 and also has two distinct factorizations. But s pi is smaller than s, meaning s would not actually be the smallest such integer. Therefore every pi must be distinct from every qj. Without loss of generality, take p1 less than q1, consider and note that 1 less than q2, t less than s. Therefore t must have a unique prime factorization. By rearrangement we see, here u equals is positive, for if it were negative or 0 then so would be its product with p1. But that product equals t which is positive, so u is either 1 or factors into primes. In either case, t equals p1 u yields a prime factorization of t, which we know to be unique, so p1 appears in the prime factorization of t. If equaled 1, then the prime factorization of t would be all q's, which would preclude p1 from appearing. Thus is not 1, but is positive, so it factors into primes. Equals. This yields a prime factorization of which we know is unique. Now, p1 appears in the prime factorization of t, and it is not equal to any q, so it must be one of the r's. That means p1 is a factor of, so there exists a positive integer k such that p1k equals, and therefore but that means q1 has a proper factorization, so it is not a prime number. This contradiction shows that s does not actually have two different prime factorizations. As a result, there is no smallest positive integer with multiple prime factorizations. Hence all positive integers greater than 1 factor uniquely into primes. Generalizations. The first generalization of the theorem is found in Gauss's second monograph on biquadratic reciprocity. This paper introduced what is now called the ring of Gaussian integers, the set of all complex numbers a plus by where her and b are integers. It is now denoted by he showed that this ring has the 4 units plus or minus 1 and plus or minus I, that the non-zero, non-unit numbers fall into two classes, primes and composites, and that the composites have unique factorization as a product of primes. Similarly, in 1844 while working on cubic reciprocity, Eisenstein introduced the ring, where is a cube root of unity. This is the ring of Eisenstein integers, and he proved it has the 6 units and that it has unique factorization. However, it was also discovered that unique factorization does not always hold. An example is given by, in this ring one has examples like this cause the notion of prime to be modified. In it can be proven that if any of the factors above can be represented as a product, e.g., 2 equals ab, then one of A or B must be a unit. This is the traditional definition of prime. It can also be proven that none of these factors obeys Euclid's lemma, e.g., 2 divides neither nor even though it divides their product 6. In algebraic number theory, 2 is called irreducible in but not prime in. The mention of is required because 2 is prime and irreducible in. Using these definitions, it can be proven that in any ring a prime must be irreducible. Euclid's classical lemma can be rephrased as, in the ring of integers every irreducible is prime. Important examples are polynomial rings over the integers or over a field, Euclidean domains and principal ideal domains. In 1843, introduced the concept of ideal number, which was developed further by Dedekind into the modern theory of ideals. Special subsets of rings. Multiplication is defined for ideals, and the rings in which they have unique factorization are called Dedekind domains. There is a version of unique factorization for ordinals, though it requires some additional conditions to ensure uniqueness.